All right. So let's talk torques. Okay. What forces do we have that are acting on it? Gravity. Okay. So we've got gravity. Gravity is acting at the middle, right? Okay. And that force is going to be m times g. How far is that away from where the pivot point is? L over 4. Okay, so this is L over 4 from the pivot. Okay, over here, we've got mg. How far is that from the pivot? 3/4. So 3L over 4 from the pivot. Okay, so pivot is right here. Okay, and then we've got 2mg. That is L over 4 from the pivot. Okay, so any force that is to the right of that pivot point is going to cause it to rotate clockwise or counterclockwise? Clockwise. Okay, so this is going to cause it to rotate clockwise, and then this one is going to cause it to rotate counterclockwise. Okay, so positive here, negative here, negative here. Okay, so if we're looking at the sum of the torques, we're going to have 2mg times L over 4. We're going to have minus mg L over 4. And then minus mg 3L over 4. The same thing we were doing last week, except last week we were able to say that they were equal to 0 because it was an equilibrium. Okay? So here we got 2mgl over 4 minus mgl over 4 minus 3mgl over 4. 2 minus 1, negative 1. Nope, positive 1. Minus 3, negative 2. So we end up with negative mgl over 2. Any questions about how I'm getting the sum of the torques? Okay, 2/4 simplified down to negative 1/2. All right, so now I want angular acceleration. Okay, and I know that the torque is equal to the inertia times angular acceleration. It's Newton's second law, rotational force. Okay, so if I want the angular acceleration, it's going to be the torque divided by the rotational inertia. Now, here's where it gets complicated. To find the rotational inertia, we've got to find the rotational inertia of the whole system. Okay? There are how many components to this system? 3. Okay? So if I want the total rotational inertia of this, I've got the rotational inertia of the rod plus the rotational inertia of the 2m block plus the rotational inertia of the 1m block. Systems consisting of 3 parts. Okay? Do you want to do the easy ones first or the hard one first? Hard one first? Okay. So, if I have a beam or a rod, the rotational inertia about the center of mass is 1/12 ml squared. And you are like, rightly so, but where did that come from? Where did that come from? There's a table in the book. And we did this in class. Okay, now if your mind's not thinking that, that's going to be really hard. You're going to have to like go through all the steps to get that, and you don't really want to go through all the integrating that is associated with that, because we went through that proof in class. Are we rotating, though, about the center of mass? No. Are we rotating about something parallel to the center of mass? Yes. So we're going to bring out parallel axis theorem. Okay? We're going to have this 1/12 ml squared, plus we're going to take the mass times the distance squared. How far are we away from the center of mass up here? L over 4. Okay? So D is L over 4. That's the distance from the center of mass to the pivot. So for our rod, we're going to go 1/12 ml squared plus m times L over 4 squared. 1/12 ml squared plus 1/16 ml squared. A little common denominator action here. You can end up with this as 7 over 48 ml squared. Now, this is just the rotational inertia of the rod. That's what this is right here. Okay? If I want the inertia of the 2m block, that's going to be 2m times what? Okay, so if I want inertia, there's the old, like the integral one is if we have like a single object, we have a beam, we have a plate, whatever. If we're talking about a system where we have just multiple masses in it, we're taking the mass and we're multiplying it by the distance squared, right? So we're thinking of it as the sum of the mass times the distance squared. The distance here is L over 4. So overall here I get ml squared over 8. Again, L squared over 16 times 2. For the 1m block, that's m times 3L over 4, because that's the distance squared. So I get 9/16 ml squared. My total, I, 7/48 plus 1/8 plus 9/16 ml squared. That's 7/48 plus 6 over 48 plus 27 over 48 ml squared. It's 40 over 48. Simplifies to 5/6 ml squared. If you can do this problem, you get all of Unit 5. That's, I mean, basically, or at least the last 4 sections. Okay, so where are we at? Taking stock in this. We're using this. Angular acceleration is equal to the torque divided by the total rotational inertia. This is the torque up here. This is the inertia. So if I want alpha here, I'm going to take negative mgl over 2 divided by 5/6 ml squared. So negative mgl over 2 times 6 over 5 ml squared. The m's cancel. One of the l's cancel. And you end up with, cancel out a factor of 2 here. We've got negative 3g over 5l. Final answer. Done. I recorded that.